Hello everyone. Welcome back. So in this video, we are going to really think about the physical chemist's way of explaining and defining and using work and heat. And so again, this is in chapter 7.1. We're going to be in this section for a while. And I'm going to go into a bit more depth than what your textbook covers. Okay, so the main form of work that we are going to think about this semester is pressure volume work. Now, the physicists tell us that work is force multiplied by distance. And that works great for a mechanics class whenever we have things sliding down a inclined plane or things swinging from a pendulum. Our molecules are a bit smaller, and while mechanics applies here, it's not really it's the governing forces, but the way that we think about it in physics class isn't really as applicable whenever we start thinking about molecules and where the energy and what is work whenever we think about molecules. So if we start with our physics definition of work, where we've got force, mass times gravity, times distance, which we're going to call h, and we play a little trick and we divide the force by area and we multiply the height by area. So we're basically multiplying by a fancy 1. Then this mg over a, it is equal to the pressure. And this h times a is equal to the change in volume. And so we can visualize this as a system that starts with a movable piston. So this piston can move up and down. It starts at this low level and something happens. Say a reaction happens or we heat it up. And the gases expand and the height of this piston changes by a factor h. And this P delta V that's happening, this is work. Now, the key here is that this P is the P external. And so the P external is the pressure. Notice that there's not really a lid on here, or there is a lid and the pressure is from the elephant. Either one. But the P external is this pressure that is pushing down on the top of the piston, either from the elephant inside of a sealed container or from the atmosphere from a non-sealed container. Whereas this delta V, this is the change in volume of the system. And so we would be looking at V final and V initial. So in this relationship with this P external is a single value. And so this relationship is only true if and only if the external pressure is constant. This is because work is not a state function. It's an inexact differential. And so really, we can think of work, because the path is important, as the sum of taking some infinitely small steps to go from our initial point to our final point. And so if we think about our P initial is here, our P final is here, and we wanted to find the work, what we can do is take small steps along this change in volume and add up the results from each of those. And this is sort of a way to figure out the path of the function to get the integral, rather than talking about just the final and the initial. And so this delta V, the small steps, is really key with work. So in reality, all realistic processes are what we call irreversible. So we're saying that once this gas inside the piston expands and the piston moves up, there's not an identical mechanism that's going to get all the gases to compress and move the piston back down. And so this integral of starting V initial going to V final of negative P times dV, this is true for all realistic processes, irreversible processes. But what we do because the math of the irreversible process is nearly impossible. Our math is hard. So what we do is we create this process known as a reversible process. It's a fictitious process where the expansion is performed very slowly so that pressure, that P external, is approximately equal to the internal pressure because we're moving this piston just ever so slowly. And so that means that to find this P external, which figuring out how much pressure comes from our elephant is rather tough. But figuring out our pressure in here, in our system, is not so bad because we can use the ideal gas law. And so if we assume that we have a reversible process, we can make the approximation that this external pressure and this internal pressure are equal to each other. And this is only true for reversible processes, which, like I said, are not realistic, but they're a model that we like to use. And it means that the math is doable. And so most of the things that we will work with are going to be reversible processes. So heat is also an inexact differential. It's not a state function. And we've kind of been talking about heat a little bit through our heat capacities. So to determine heat, we have a few different equations that we've already gone through, where dq is equal to cv dt at constant volume, dq is cp dt at constant pressure, and then we have a reversible process that we need to define because it's very possible that constant volume or constant pressure or is not really useful for us. And so when we have a reversible process, dq reversible is TdS. And remember, just like with the volume case, reversible processes really don't exist. But what we're going to do is we're going to take small enough steps that the total entropy of the system remains constant. And so these DS's are super small steps. And so we can say that the number of microstates that we're changing with each step is really very small. And we can assume that that total entropy is staying constant. So why are we even talking about this? We are talking about this because of the first law of thermodynamics. And this is where we are going for Monday's videos. And the first law of thermodynamics is talking about how the system and the surroundings exchange energy and work with each other. And so in this case, our system is in the blue, our surroundings is the elephant, and the system and the surroundings are transferring heat and work. And these are the two forms of energy that are being moved through their processes. And so in this case, since we're adding heat to the system, the surroundings, which are flame down here, is also surroundings. Our surroundings are giving heat to the system. And in doing so, it heats up the system, which causes the gases to expand, and it causes this piston to raise. And that means that the system is doing work on the surroundings. And we're going to go more in depth into how do we know which way the work and the heat are going. And we're going to go more into what this dE equals dQ plus dW and how we quantify this heat and energy transfer between the system and the surroundings. Okay, so more to come. Over the next week, we are going to really finish up the first law of thermodynamics and really understand how this energy transfers and how we measure this energy transfer.